In this section, we will be covering inverse functions. So our objectives are going to be to determine whether a function is one-to-one, and if it is, find a formula for its inverse. And B, we want to simplify expressions of the type f circle f inverse of x and f inverse circle f of x. So to find the inverse of a function, or of a relation, we interchange the inputs, which is usually x, with the outputs, which are usually y. This produces the inverse of the relationship. So, for example, before we do the ones that are on our handouts, if we had the following t-table, x, and our relationship was to add 5, if I use the input 1, well, 1 plus 5 gives me 6. If I put in 5, 5 plus 5 gives me 10. If I put in 6, 6 plus 5 gives me 11. And if I put in 10, 10 plus 5 gives me 15. So, according to this, if we find the inverse, it says we interchange our inputs and our outputs. So all of our outputs, the second column becomes our inputs, so that's 6, 10, 11, and 15. And our outputs are going to be 1, 5, 6, and 10. And so something we know is the inverse of adding 5 is to subtract 5, and let's check. So if we went down this, if we look at our first column, 6 take away 5 is indeed 1, 10 take away 5 is 5, 11 take away 5 is 6, and 15 take away 5 is 10. So this is an example of what we're going to be doing in general. Alright, so let's take a look at this relation that we have right here. So it says find the inverse of the relation, and we have the set of ordered pairs 5, negative 10, 0, negative 3, and negative 4, 4. So to find the inverse, we interchange all of our inputs and our outputs. So our first ordered pair becomes negative 10 and 5. Our second ordered pair becomes negative 3 and 0. And our last ordered pair becomes 4 and negative 4. Alright, it's now your turn. So go ahead and find the inverse of this relation. So once again, you're going to interchange your inputs and your outputs. So we'll have 13 pi and 2, and they get paired with negative 2, 3, and 5, respectively. All right. So to find the inverse of an equation, we're going to continue what we've been doing. will interchange the input variable and the output variable. So let's take a look at our next example. So we want to find the inverse of this relation. So all of our x's are going to become y's, so we get y to the 6th power times the square root of our y becomes an x is equal to 5. And that would be the inverse of that equation. All right, it's now your turn. So go ahead and find the inverse of this relation. Once again, we're going to interchange all of our variables. So we get x is equal to 6y squared minus 6y plus 1. All right, so let's take a look at our next example, and we want to explore this concept graphically. So the graph of the equation f of x equals x squared minus 6x is shown below. Reflect the graph f of x across the line y equals x to obtain a graph of its inverse. So if we look at the vertex of this parabola right here, its vertex is located at the point 3, negative 9. So if we interchange our x and our y, we're going to get the point negative 9, 3, which is right here. And if we get a couple more points, I have this point and this point. So that's going to give me 4 and negative 8, and it's going to give me 2 and negative 8. And if I come up here, I'm going to have negative 8 and 2 and negative 8 and 4. Then we have a very interesting point right here, which is the point 0, 0. And if I interchange 0 and 0, I end up with exactly the same point. So I also get 0, 0. And if I grab this point right here, I am at 6, 0. So that's going to get paired with 0, 6. So I get something that looks like this. And we'll notice that in this graph, these points are perpendicular to the line y equals x when we connect them on this. So we get a mirror reflection, and if you can imagine, you could fold this graph across that line, and the inverse and the graph would land exactly on top of each other. So we have the following observation, that inverses are symmetric with respect to the line y is equal to x. All right, we'll come back to this picture in a minute, but let's grab a couple of definitions. So, first definition is of a one-to-one function. So, a function is one-to-one if when f of x is equal to f of y, then x really had to be the same as y. So let's talk about what this definition means. So it says if a function is 1-to-1, if when we have two outputs that are the same, that we really didn't have two outputs. What it's saying is that those two outputs were really the same output because the inputs had to be the same. So in other words, it's saying that each output is unique. So the key idea then is if each output is unique, then the outputs can't repeat. So that means that any y value can occur at most once. So let's give an example of a not one-to-one function. So if we have f of x equals x squared, this is not one-to-one. And we can verify this because if I go f of -2, I would have -2 squared, which is +4, and then I can also check f of 2, which is 2 squared, which is going to give me 4. So the inputs x equals -2 and x equals 2 have the same output. Namely 4. So this is not a one-to-one function. So graphically, this can be summarized in what we call the horizontal line test. So the horizontal line test is the cousin of the vertical line test. So remember, the vertical line test says if any vertical line can be drawn that intersects a graph more than one time, then the graph does not represent a function. So the horizontal line test is similar to that, but it is to test for one-to-one. And it says if every possible horizontal line intersects the graph of f of x at most once, then f of x is a one-to-one function. All right, so let's keep this definition in mind and let's look back at example 3. So if I were to draw a horizontal line, so right here, we'll notice this horizontal line touches the blue graph twice. So this is not one-to-one because it fails the horizontal line test. And notice something very interesting happens. If you reflect a horizontal line across the line y equals x, well, the reflection of a horizontal line becomes a vertical line. So that means this vertical line intersects the inverse twice, which would then mean that the inverse is not a function. So we'll come back to that in just a moment, but that's kind of the big idea where we're going with this. So let's take a look at our next example. So we wish to determine if f of x is 1 to 1. So if we want to determine if this function is 1 to 1, the simplest way to do so is to just graph it. So if we grab our graphing calculator and we go y equals, and we go x to the 6th power minus 2x cubed plus 1, and we go graph, we get something that looks like this. So based on this graph, I can draw a horizontal line, touches the graph more than once, so this fails the horizontal line test. So it is not 1 to 1. All right, it's now your turn. Let's take a look at our next one. So similarly, I want you guys to go ahead and determine if this function is 1 to 1. So we put it into the calculator, and we get x to the 5th minus 2x cubed plus 5x. We end up with a graph that looks like this, and this one appears to pass the horizontal line test. So we would say it's 1 to 1. So the reason that we really like 1 to 1 functions is the following. Well, we have a theorem, and it says if f of x is a 1 to 1 function, then the inverse of f of x exists, and is a 1 to 1 function. Alright, so then there's some notation we need to discuss that goes with this. So the inverse of f of x is written as f, and where we would normally put an exponent, we'll put a minus 1, and then we have a parenthesis x. The symbol is red as f inverse of x. So then this, what looks like an exponent, isn't, is the inverse, and then the parenthesis x is just like we had with a regular function of x. So as mentioned, and it is worth a warning, is the -1 is not an exponent. So what that means is that f inverse of x is not equal to 1 over f of x. All right, let's take a look at our next example, and we'll outline some steps as we do it. So it says determine if f of x is 1 to 1, and if it is, find a formula for its inverse. So let's go ahead and check if it's 1 to 1. So we have 3x over x take away 3, and we graph. And our function appears to pass the horizontal line test. Alright, so then to find the inverse of a function, we're going to do the following 4 things. So step 1, we're going to replace f of x with y. So that gives us y equals 3x all over x minus 3. Then step 2, which is the same one we were doing above, we are going to interchange our inputs and outputs. And in this case, that's going to be x and y. So we get the new equation, x equals 3y all over y minus 3. Then our next step, step 3, is we're going to solve for y. So this is a rational equation in y, so we need to clear our fractions by multiplying by the LCD. And our LCD in this case is just y take away 3. So on the right hand side they reduce out, and that leaves us with y minus 3 times x. And we open our parentheses by distributing, so we get xy minus 3x is equal to 3y. And we need to solve this equation for y, so we need to get all of our y's on one side and everything without a y on the other. So I minus 3y, a minus 3y. I'm going to add 3x. I'm going to add 3x. And these reduce out and these reduce out, and that leaves the equation xy minus 3y is equal to 3x. And then I'm going to factor out my common factor of y. And that leaves x minus 3 times y is equal to 3x. And then finally, to isolate y, I divide both sides by x take away 3, giving y equals 3x all over x minus 3. So now finally, we're at the very last step, which is step 4, and we are going to replace y with f inverse of x. So then our final answer is going to be f inverse of x is equal to 3x all over x minus 3. And you might be saying, well, hey, wait a minute, Professor Peterson. When I go back to the very, very beginning, that was our original equation, was 3x over x minus 3. So it does turn out that this function is its own inverse. And that can happen. It doesn't always happen, so you shouldn't assume that this is going to happen. But it is indeed possible for a function to be its own inverse. So let's take a look at a couple of things before we move on to the next example. So what is f circle f inverse of x? Remember, the circle operator is function composition, which means we are going to put the second function into the first function as an input. So f of f inverse of x. And that means everywhere where I see an x in f, I'm going to put my entire function f inverse. So that means I'm going to replace every x in f with the entire function f inverse. So then f of f inverse is going to be 3 times, I replace x with what it's equal to, which is 3x all over x minus 3, divided by, and then I have x minus 3, so I'm going to get 3x all over x minus 3, take away 3. Okay, well now I need to simplify this down a little bit. So I have a compound fraction, and I notice that my LCD for all of my fractions is x minus 3. So to simplify this up a bit, I'm going to do 3 times 3x in the top gives me 9x all over x minus 3 divided by, I have 3x over x minus 3 minus 3. So remember, to simplify a compound fraction, we multiply the numerator of each fraction by x minus 3. So I'm going to multiply this by x minus 3. I'm going to multiply this by x minus 3, and I'm going to multiply this by x minus 3. Because I'm multiplying the top and the bottom of the entire fraction by the same thing. So when I do this, in the numerator, those reduce out. Here, these reduce out. And I'm left with 9x over 3x minus 3 times x minus 3. When we multiply by the LCD, it always reduces out all of our compound fractions. So now we just need to simplify. So we have 9x over 3x minus 3x plus 9. And then we have a positive 3x and a negative 3x, so they add to 0, so they reduce out. And then we're left with 9x divided by 9. And now the 9's reduce out. And after all of that, we get back x. Turns out that that is always going to be the case. So in general, we have that f circle f inverse of x is going to equal x, and it also happens in the reverse order. The f inverse circle f of x is also going to equal to x. So a function and its inverse undo each other under the operation of composition. All right, it's now your turn. I want you to go ahead and find the inverse of 3x plus 7. So we do our same 4 steps. So 1, we replace f of x with y, so we get 3x plus 7. Step 2, we interchange our x and our y. Step 3, we solve for y. So I minus 7, I minus 7. That gives me x take away 7 equals 3y. Divide by 3, divide by 3, divide by 3, writing it in the other order, that gives us y equals 1/3 x, take away 7/3. And then finally, we replace y with f inverse of x, and we get f inverse of x is equal to 1/3 x, take away 7/3.